BigO analysis. BigO analysis is a standard analysis which is used to analyze the programs. When we want to analyze the programs, we will analyze it in two perspectives. One is the time complexity and the space complexity. Time complexity is the time that is required to run the program. Space complexity is the extra amount of space that is required to um, complete the program. So here we will compare recursive call, tail recursive call and iterative call. We will compare the BigO analysis of these three. Let's say we have written two algorithms to solve the same problem. Just now we have seen we have written two algorithms for factorial, one using recursive and one using iterative. We want to find which one is better. In that case, as I said, we will compare time complexity and space complexity, where time complexity is the time taken by the algorithm to run and the space complexity is the amount of memory, extra amount of memory required by the algorithm. BigO means the order of growth of a function. The growth of any complexity function for large input size values depends on the most significant term of the function. So the less significant terms are dropped from the function. Actually, when we are writing these programs in real life, when we want to do some computations, we take the value of n as some millions, actually millions or thousands or lakhs. We do not take as n equal to 5 or n equal to 10. So in those cases, the time complexity and space complexity is very important to determine the best program to write the code. I have taken three examples to understand what is the BigO notation. Let's say a function is defined as t of n is equal to 3n square plus 6n plus 7. So what is the BigO notation? Here what we will do is we will take the most significant term and the less significant terms are ignored. If n is equal to 1, this value is 3 plus 6 plus 7. But let's say n is equal to 1000, that is 3 into 1000 square plus 6000 plus 7. 3 into 1000 square is very big compared to 6000 plus 7. So we will ignore the less significant term 6 and 6 plus 7 and we will take the BigO function as the order of n square. Similarly, if we have a function 6n cube plus 4n square plus 5n plus 100, we will consider the BigO as order of n cube. And another function t of n equal to 2 power n, which is an exponential function, plus n square plus 6, then we will take it as the order of 2 power n. So this is how we will consider the BigO of a function. There are different types of BigO functions. That is, order of 1 is a constant function, order of logn is a logarithmic, order of n is a linear function, order of n log n, order of n square is a quadratic function, order of n square log n cube 2 power n is an exponential, and order of n factorial is a factorial function. So we can see when we draw a graph between n and order of n, we can see that order of 1 is a constant time function. It is a horizontal line, whereas order of n increases with the value of n, so that is a linear function. Here we can see the graph. So the rest of the functions are given here. What we can observe is order of n factorial 2 power n and n square, the performance is not very good. That's why it is indicated in pink color. And order of n log n is better than these functions, but it is bad when compared to the other functions like order of n, which is a fairly better function, and order of log n and order of 1 are the best functions. So when we want to write a program, let's say the let's say the order of the function is exponential, and if there is a way exponential in the sense order of 2 power n. If there is a way to write it as order of log n, we should try to write a program with order of log n so that it is more efficient. How to calculate BigO? Order of 1. When we take a variable integer a is equal to 100, it is actually the time complexity is order of 1. When we take a for loop, a for loop has an order of n, but here in this for loop what we are considering is we are not increasing the I value by I equal to I plus 1, we are increasing the value by I equal to I into 2. I will just use some already written code to understand these functions. They are very simple to understand actually. Here we can see, let's say when n equal to 8, when there are 8 input values, I equal to 1, I less than n, and I is increasing as I is equal to I into 2, then how many times hello will be printed? Here we can see is that hello is printed only 3 times. 3 times for I equal to 1, I equal to I into 2, I into 2. For I equal to 2, I equal to I into 2, 2 into 2 equal to 4. So for 1, 2, 4 these values I is printed. So n is equal to 8, and we are actually doing 3 operations. That implies this is a function of order log n, log 8 to the base 2. 8 is nothing but 2 cube. Log 2 cube to the base 2 is 3. So this is order of 3. That is nothing but order of log n to the base 2. So we can see this is a function of order of log n when I is increasing as I equal to I into 2. Order of n, I have already mentioned a for loop is a function of order of n. We will just look at this, we will just look at the code of this. Then order of n log n. So we will look at these two functions at a time. So when n is equal to 8, this is for order of n. I equal to 0, I less than n, I is I plus 1. Then we run this program, hello will be printed 8 times. See, hello is printed 8 times, starting from 0, ending at 7. So that implies if n is equal to 100, hello will be printed 100 times. So the number of operations are proportional to the number of inputs. So this is a function of order of n. Next we look at order of n log n. There are 2 loops here. Whenever there are 2 loops, 2 nested loops, what we do is we will multiply the order of one loop with the order of another loop. Let's say there is a for loop inside a for loop. The order of for loop is n. So we multiply n into n for each for loop. So then that becomes an order of n square. We will just look order of n square also. But here we are looking at order of n log n. This loop for j equal to 1, j less than 8, j equal to j into 2 is similar to the one we just looked at, that is order of log n. And for int I equal to 1, I less than n, I plus plus is similar to the one of order of n. So order of n, n into log n, that is order of n log n. We'll see how many times hello will be printed. Here we can see order of n log n. Log n is nothing but log 8 to the base 2, that is 8 2 power 3 is 8, 2 power 3 to the base 2, that is 3. 3 into n is 8, so 3 into n into log n. 3 into log n is n is 8, log n is 3, so 3 into 8 24. So hello is printed 24 times. This is 3 times. 1 is printed 3 times. It is printed till 8. So 8 into 3 is 24. So this is of order of n log n. Here this inner loop is running from j equal to 1 to n, j plus plus order of n. Loop is running from 1 to n I plus plus order of n, n into n is n square. So this will run for how many times? N into n is 8, 8 into 8 is 64 times. So previous loop has run for 8 into 3 24 times. So 24 is better than 64. So order of n log n is better than order of n square. Here we can see 1 is printed 1 2 3 4 5 6 7 8. 1 is printed 8 times. So 8 is printed 8 times. So 1 to 8 into 8, it is printed 64 times. If you want to reduce the count, reduce the number and want to see the count, we can print like this, and equal to 2. So 2 into 2, it will print 4 times. See, it has been printed 4 times. So from these, what we can understand is order of n square for n equal to 8 is 64 times. 64 operations will happen. Order of n log n is 24. So order of n log n is better than order of n square. And order of log n is log 8 to the base 2, that is 3. So order of log n is better than order of n log n. And order of n is 8. So order of log n is better than order of n. And order of 1 is nothing but constant time space. For constant time space, let's say n equal to 2. Let's say we are just trying to print n. So we'll print it once. So that is order of 1. That is a constant time. So let's compare these BigO notations. Order of 1 log n, n log n, n square, 2 power n. If we write the codes similarly for int I equal to 1 and I less than or equal to math dot power 2 power n, if n equal to 2, 2 square, 4 times will be printed. For n equal to 8, it is 2 power 8. 2 power 8, I think it is 512 times. So order of n factorial is again 8 factorial. 8 factorial is a bigger number. So comparing these numbers, we can actually say that the relative time complexity of different BigO functions are order of n factorial is greater than order of 2 power n is greater than order of n cube is greater than order of n square is greater than order of n log n is greater than order of n and order of log n and order of 1. Let's just try to see the values actually for n equal to, I'll take a smaller number for n equal to 2, okay, I'll take for n equal to 2, then we'll understand what are these values. Okay, 2 factorial is 2, 2 power n, 2 square is 4, n cube, 2 cube is 8, n factorial, 2 power n, n cube, n square is nothing but 4, n log n is 2, and log 2 to the base 2 is 1, it is 2. Order of n is again 2. Order of log n, log 2 to the base 2 is 2. Order of 1 is 1. Order of 1 in the sense it can be any constant number. This we have taken for n equal to 2. Let's say we want to take these values for n equal to 8. So order of 1 will be 1, log 8 to the base 3 is log 8 to the base 2 is 3, n is equal to 8. 3 into log 8, 8 into, sorry, n log n, 8 into log 8 is 8 into 3, 24. N square, 8 square is 64. N cube is 8 into 8 into 8 is 512. 2 power n, 2 power 8. 2 multiplied 8 times. You multiply 2 4 times. 16 into 16. That is 256. And n factorial. 8 factorial is 8 into 7 into 6 into 5. 4, and 4 factorial is 24. Yes. Now we can see that order of 1 is better than log n, that is better than order of n, that's better than n log n square. 2 power n is better than n cube. Here you can see 2 power n is better than n cube, and the last is the n factorial. So this is how we understand BigO notation. And while computing our programs, while computing our programs, we have to calculate the BigO notation of the program and try to see if there is a better way to write the program. Space complexity is amount of extra memory required by the algorithms. We'll look at it in detail while we do searching and sorting algorithms, which are the next topics in the algorithms module. So now finally we will do the BigO analysis for recursive call, tail recursive call and iterative call, and end the session on recursion.